Welcome to our exploration of Charles's Law. In this presentation, we'll uncover how temperature and volume are connected for gases at constant pressure. This fundamental concept will help us understand various real-life applications and solve practical problems involving gases. Charles's Law describes the relationship between a gas's volume and its absolute temperature when pressure remains constant. Simply put, as the temperature of a gas increases, so does its volume. Mathematically, we express this as V directly proportional to T, or V equals kT, where K is a constant. This proportionality forms the basis of many scientific and industrial applications. When the state of a gas changes, Charles's Law helps us relate the initial and final conditions. The formula V1 over T1 equals V2 over T2 allows us to calculate the volume or temperature after a change, provided pressure stays constant. This equation is a powerful tool for solving gas-related problems. This graph shows the direct proportionality between volume and temperature for a gas. When plotted, the volume increases linearly with temperature, forming a straight line that passes through the origin when temperatures are measured in Kelvin. This highlights the clear relationship described by Charles's Law. The science behind Charles's Law lies in the behavior of gas particles. Heating a gas increases the kinetic energy of its molecules, causing more collisions with the container walls. These collisions force the gas to expand, increasing its volume. On the flip side, cooling the gas reduces its kinetic energy, leading to a decrease in volume. For Charles's Law to hold true, specific conditions must be met. The gas must behave ideally, meaning its molecules experience negligible interactions. The pressure must remain constant throughout the process, and all temperature measurements must be converted to Kelvin, the absolute temperature scale. Charles's Law isn't just a theoretical concept, it's highly practical. For example, in hot air balloons, the heated air expands, increasing the balloon's volume and enabling it to rise. Whether balloons expand and contract as they ascend or descend with changing temperatures. Similarly, automobile tires lose pressure in colder temperatures as the air inside contracts. Solving problems using Charles's Law involves a few simple steps. First, ensure all temperatures are in Kelvin. Then, apply the formula. Rearrange the formula to find the unknown variable, whether it's the initial or final volume or temperature. Let's apply these steps in some example. Let's solve an example problem step by step. We are given that a gas occupies a volume of 300 cubic centimeters at a temperature of 27 degrees Celsius. We are tasked to find the volume of the gas at a temperature of 127 degrees Celsius. Assuming that the pressure remains constant, the first step is to convert the temperatures from Celsius to Kelvin, as required by Charles's Law. Recall the conversion formula. Kelvin equals Celsius plus 273. For the initial temperature, T1 T_1 we have 27 degrees Celsius plus 273, which equals 300 Kelvin. For the final temperature, T2 T_2 we have 127 degrees Celsius plus 273, which equals 400 Kelvin. Next, we use the formula for Charles's Law, which states, the ratio of the initial volume to the initial temperature equals the ratio of the final volume to the final temperature. Substituting the known values into the formula, 300 cubic centimeters divided by 300 Kelvin equals the final volume, V2V_2V2, divided by 400 Kelvin. To solve for the final volume, V2V_2V2, we multiply both sides of the equation by 400 Kelvin. This gives us V2V_2V2 equals 300 cubic centimeters times 400 Kelvin, divided by 300 Kelvin. Performing the calculation, 300 times 400 equals 120,000. Dividing by 300 gives us 400 cubic centimeters. Thus, the final volume of the gas is 400 cubic centimeters. Now let's move on to another example. A gas initially occupies a volume of 500 milliliters at a temperature of 200 Kelvin. The gas expands to a volume of 750 milliliters, and we are to determine the final temperature in Kelvin. Using Charles's Law, We know that the initial volume divided by the initial temperature equals the final volume divided by the final temperature. Substituting the given values into the formula, 500 milliliters divided by 200 Kelvin equals 750 milliliters divided by the final temperature, T2T_2T2. To solve for T2T_2T2, we first cross-multiply. This gives us 500 milliliters times T2T_2T2 equals 200 Kelvin times 750 milliliters. Simplifying the right-hand side, 200 times 750 equals 150,000. Now, divide both sides by 500 to isolate T2T_2T2. We have T2T_2T2 equals 150,000 divided by 500. Performing the division, 150,000 divided by 500 equals 300 Kelvin. Finally, to convert the temperature to Celsius, subtract 273 from 300. This gives US 300 minus 273 equals 27 degrees Celsius. Therefore, the final temperature of the gas is 300 Kelvin, or 27 degrees Celsius. In summary, Charles's law provides a vital link between the volume and temperature of gases at constant pressure. By understanding and applying this law, we can predict the behavior of gases in various conditions, solve related problems, and appreciate its numerous real-world applications. Thanks for watching. To deepen your understanding of SI units, explore our comprehensive resources, including revision notes, past questions, gamified quizzes, and workbooks. These tools are designed to help you master the concepts effectively and enjoyably.